Welcome to the sixth lecture in the series on sequences of functions. You might have studied the convergence of sequences of real numbers. One of the most important theorem there is the so-called Cauchy criterion. A sequence of real numbers is convergent if and only if it is Cauchy, right? So the advantage of this theorem is sometimes we are just interested in knowing whether the given sequence is convergent, sequence of real numbers is convergent. Okay, in fact, sometimes we may even define a real number as by the limit of the sequence. For example, let us start with summation 1 upon k factorial, k running from 0 to n. Then you know it converges by whatever test you want, right? And therefore it converges to a real number. That real number is what we denote by E in a POC, right? Euler's thing. So this is how it will be defined. So a similar question we can ask about uniform convergence. Given a sequence of functions, I may not be able to say whether f1 converges uniformly to a given function f because I may not be able to identify that function, but I may be able to say whether it is uniformly convergent, right? So is there any kind of Cauchy criterion for uniform convergence? That's the question we want to investigate today. Are you ready? Let's get started. So, but as usual, let's start with the simplest question. I have set x and I have a sequence of real numbers, sequence of functions fn, and what I want to know is whether there is any Cauchy criterion for pointwise convergence. Okay, what does that mean? That means for every x in x, right, I want to know whether the sequence f and x converges. But because our knowledge about real sequences, we know this happens if and only if the sequence for every x in x, the sequence f and x is Cauchy. That's it. Okay, so fix an x in x, and suppose I know fn of x is Cauchy. Okay, this is a sequence of real numbers. Okay, fix. Therefore fn of x must converge to some number. That number will depend upon x, so I will call it f of x. So I have find a function f from x to r. By very construction fn converges to a pointwise, right? So what is the Cauchy criterion for pointwise convergence? For each x, the sequence fn x is Cauchy, sequence of real numbers. But let's try to write it in terms of your usual epsilon capital N notation, right? So what does it mean? For every x in x, I want fn of x to be Cauchy. This is a condition. So let us expand this. For every x in x, what do I want? You give me any epsilon positive, there is a capital N. This N will depend upon epsilon as well as the number x, because the sequence depends upon x, right? So that what happens? For every n greater than or equal to capital N, modulus fn of x minus fm of x should be less than epsilon. 1, 2, 3, 4. Is that clear? What does this say? After for every x in x, whatever within brackets, it simply says fn x is Cauchy, right? You are fixed on x. After that, you want to say fn x is Cauchy. What is the definition? For any given epsilon, there is a natural number, so that for every m and n greater than or equal to n, the mth term and nth term are at a distance at most epsilon. That's what you have done. Okay, right? So if a sequence is convergent, we know that pointwise convergent, right? Now you want such a criterion for the sequence to be uniformly convergent. So what you should expect? You had already learned uniform convergence using the quantifiers, right? Do you remember? What did I observe there? This for all x comes here in the case of uniform convergence. right? But let's go slow, let us understand. Okay, suppose Fn converges uniformly to f on x. What does this mean? This means for every epsilon positive there is a natural number. Okay, so that for every n greater than or equal to capital N, modulus Fn of x, and sorry, for all x in x, modulus Fn of x minus f of x is less than epsilon. Yeah, right? Now suppose m and n are greater than or equal to capital N. Let us see what happens. Now I want to know, and no matter what x I take, let us look at fn x minus fm x, right? I want to find some kind of an estimate. Do I know that? I may not know, but what I know is, since n is greater than or equal to n and m is greater than or equal to n, I know how to estimate mod fn or mod fm minus fx. I know how to estimate. Therefore, what is the thing? So obvious thing is to do this, fn x minus fx plus mod fx minus fmx, right? What do I know about this? For every x, this fellow is less than epsilon. So if you want, I could have taken epsilon by 2. Anyway, epsilon plus epsilon. You understood that? So what did I find? I found that given any epsilon positive, so suppose I made this epsilon by 2, then what happens? So given any epsilon positive, okay, there exists a capital N, so that this happens, right? And hence what happens? For every m and n greater than or equal to capital N, and for every x, mod fn x minus fmx is less than epsilon. Do you understand? This is like your usual Cauchy sequence of real numbers, except this is, the single n is going to work for all x in capital X. Do you understand? Pause, review, proceed. So I'm sure now all of you know how to make a definition. So I have a sequence fn to R. Okay, x need not be a subset of R. It could be any set, non-empty set. Okay, then I say fn is uniformly Cauchy. On x. So whenever you say uniform, the set should be specified. Uniformly Cauchy on x if for every epsilon greater than 0 there exists a natural number n. With what property? So that for every m and n greater than or equal to capital N, and for every x in capital X, mod fn x minus fmx should be less than epsilon. Okay, and look at this and compare this with this. You see that? It's exactly similar like uniform convergence. Here also for x starts with pointwise convergence. Here for x is the interior. Yeah, please pause, review, and try to write on your own now. Okay, just close this, pause the video, take a pen and paper, and see whether you can write uniformly Cauchy definition. Yeah, it will be a good thing. That will give you confidence. So what have we proved now? We have proved that if fn converges uniformly to f, then fn is uniformly Cauchy. That's what this proves. Yes, it's like what you do in sequences, real sequences. If xn is convergent, xn is Cauchy. That's the easy part. What is the difficult part? Yes, if xn is Cauchy sequence are real numbers, this is convergent. It's a deep theorem. Okay, now we are going to use it. Okay, we are not going to prove that, we are going to use that result about Cauchy completeness of R we are going to use. So what we have proved is Fn is uniformly convergent implies Fn is uniformly Cauchy. This is what you proved. Okay, so we want to know whether the converse is true. So what about the converse? That is, if I give a sequence Fn which is uniformly Cauchy, remember for uniformly Cauchy I don't have to know anything about F. Yeah, right. I want to know whether I can prove Fn is uniformly convergent. Remember, if it is uniformly convergent, there is a problem. What is the problem? I have to find the limit function F. After that I have to prove Fn converges to F uniformly. You understand that? Same problem with the sequences also. If Xn is Cauchy, is easy. If I have to say Xn is convergent, then I have to find a limit point x, limit x, and then show that Xn converges to X. Okay, right. So this proof uses what I usually call curry-leaf trick. And textbooks, many except my book, most books pass on, they use some other argument. Okay, and I find that many students are slightly uneasy. Okay, and the beginning days it's a little difficult, but that proof is correct. There is nothing wrong. What you find in other books is nothing wrong. That's absolutely correct. Okay, I will also indicate why it's correct later, but let's do that. So as I said, the proof which I want to use, okay, the trick is what I call curry-leaf trick. Why all of a sudden it doesn't write well? Yeah, okay. What does it say? This trick is some kind of, my way of doing fancy way of saying triangle inequality. Okay, it is even in metric spaces, it's true, but let me stick to real numbers now. Notice that triangle inequality usually teachers will write like this: for every x, y, z in R, okay, mod x, y is less than or equal to mod x minus z plus mod z minus y. This is what they write. Yeah, this I call a static version. I have a dynamic version. Okay, that says for every x, y in R, okay, and for any t in R, mod x minus y is less than or equal to mod x minus t plus mod t minus y. You may say, what is there? It's the same. In place of z I use t, but remember I said x and y are given and I am talking about t separately. Why? Let us try to understand this, because this is very crucial for analysis. Most often, as I keep saying, an analysis means I have to estimate something. Suppose I want to estimate mod x minus y. Okay, I want a better bound, upper bound for that. Okay, maybe even I want to say mod x minus y is less than epsilon for some given epsilon. You follow that? Yeah. What this says is I may not be directly able to prove mod x minus y is less than epsilon, but what I can do is I can find an intermediate t, so that I know how to estimate mod x minus t and I know how to estimate mod t minus y. I have an upper bound for them, and suppose mod x minus t is also less than epsilon by 2, mod t minus y is also less than epsilon by 2, then it turns out mod x minus y is less than epsilon, right? So it just says this dynamic way of saying when you want to estimate mod x minus y, make a smart choice of t. You follow that? That t is what I call curry leaf. Okay, you just use it to get what you want. The correct flavor is mod x minus y is less than epsilon. You get that flavor. Okay, after that you can ignore t, like the way you curry leaf is ignored in South Indian cooking. Yeah, you understand this? Please pause, just pause, review the thing, if necessary replay the video and understand. This is the crucial thing, right? I want to estimate mod x minus y. Then what does it say? Choose a smart t so that you know how to estimate mod x minus t and mod t minus y, and therefore you get an estimate for mod x minus y. Yeah, okay. If you had seen some of my videos on continuity or sequences, you would have seen I had used many times. Okay, the Curry-Leaf trick. Even in Riemann integration, I would have used it. Anyway, right? Okay, we can go one step further. Okay, this is very crucial for what we are going to do. Suppose I have two functions f and g from a set x to r. Right? What I want is, I want to say for every x in capital X, I want to say mod fx minus gx, okay, is less than or equal to something. Maybe again epsilon, but it could be anything. You understand this? Or strictly less than. I want to prove this. Right? Now remember, for every x this can be done. Right? Now let's look at, you can try to use a t, but what I am saying is, this is very crucial, please pay attention. What I am saying is this t can depend on x also now. You follow that? So fix x, okay, for this x find a t which will be t of x, okay, it depends upon x. Therefore fx minus gx is less than or equal to fx minus t plus t minus g of x. And suppose I know this is less than epsilon by 2, this is less than epsilon by 2, I am through. For that x I have proved mod fx minus gx is less than epsilon. But for each x, suppose I can do this. What does it mean? For each x I can find a number t. That number t may vary. Are you following? Yes? In other words, okay, I will write, I can even do something more. Please pause, review and proceed. Okay, I can do something much more also. What I say is, for each x in capital X, I can find a function which depends upon x hx such that mod fx minus gx is less than or equal to fx minus h x at x plus hx at x minus gx. And suppose I know this is less than epsilon by 2, this is less than epsilon by 2, then I know mod fx minus gx is less than epsilon by 2. And this I can do for each and every x. So what do you think I have proved? I have proved that for all x, mod fx minus gx is less than epsilon. Do you understand? Okay, this hx is your curry leaf, curry patta. I just used it to get this inequality. For each x I can do that. Therefore for each x I proved mod fx minus gx is less than epsilon. That means for every x I have proved it. Yeah, for all x I have proved it. You understand? Okay, please again pause, review. I'm putting too many pause, review, proceed, because I have seen even good analysts had problem, okay, when I just like that gave the proof using Curry-Leaf trick. Okay, that is why I break it into small pieces. Each piece is easy and you will be convinced faster, so that the final proof will become easier. Okay, sure, can I go ahead? Now I'm going to prove the theorem. What is the theorem I want to prove? Suppose f1 from x to r, okay, given, and f1 is uniformly Cauchy. Then there exists a function f from x to r so that f1 converges to f uniformly on x. What do you have seen? If f1 converges to f uniformly, then f1 is uniformly Cauchy. Now the converse is proved. Is the result clear? There is no assumption about x. Remember that x may be any set. Okay, and even if you think x is a subset of R, it need not be closed, open, compact, if you know all those kind of jargon. Okay, I don't need any of those things. Just a set is good enough for us to get it done. Sure? Okay. Now think. What is the first thing I have to do here in the proof? So first thing is I have to find a function f. How do you think I will do that? Again, remember we proved something interesting. What did we prove? If f1 converges to f uniformly, then f1 converges to f pointwise. That is, for each x, f and x must be convergent, and the limit is what? Fx. You understand? Now that suggests something. What does it suggest? if fn is uniformly Cauchy, okay, then for each x in x, the sequence of real numbers fn x is a Cauchy sequence of real numbers. Yeah, go back to the definition. Yes or no? Because you fix for every epsilon there is an n, so that you have fixed an x, so therefore for every x also fn x mod fn x minus fmx is less than epsilon. Yeah, is that clear? Now you fix an x, fn x is a Cauchy sequence of real numbers, but by Cauchy completeness of R we know that there exists a real number, okay, call it alpha, such that fn x converges to alpha. But remember that alpha, the limit, will depend upon x, so we call it f of x. Okay, so there exists a real number fx in R, so that fn x converges to f of x. Okay, this is just a real number alpha, I call it f of x. You understand? I denote it by f of x. So now I have a function f. What is the function? X to R. So what is f of x therefore? It is nothing other than limit of fn x. That's how we constructed. You clear? So we had found a function f from x to R, so that fn converges to f pointwise. What is that we want to prove? We want to prove it is convergent uniformly. Yeah, right. As usual, again I will think through the proof. Okay, I will not write the textbook proof to start with, so that you can see the power. So what is that I want to show? I want to show fn converges to f uniformly on x. What does that mean? I would estimate fn of x minus f of x. I want to say it's less than epsilon for all x, for n sufficiently large, right? Okay, I am not writing capital N, etc. all the time. So I have to find a uniform estimate for mod fn x minus fx. Do I know that? Yeah, I know. Okay, I want this uniformly less than epsilon. Do I know that? I know pointwise, because fn x converges to fx. Therefore, if you give me an epsilon, okay, there is an n, that n will depend upon epsilon as well as x. That if n is greater than or equal to capital N, mod fn x minus fx will be less than epsilon. That's all I know. But am I happy with that? No. What do I want? I want this n depend only on epsilon but not on x. Okay, this I don't want. Okay, so how do I do that? So somehow I have to make use of the fact fn is uniformly Cauchy. Yeah, so what do you think I will do? There is an obvious thing, right? This is less than or equal to fn x minus fmx plus fmx minus fx. What is the great deal? Instead of fn x minus fx, I have fmx minus fx and also m. You may wonder what is, okay, but remember this is going to be my curly leaf t. You understand? You fix x. Yeah, I want mod fn x minus fx should be less than epsilon for n greater than or equal to some number, capital N. Okay, you have to find all those things. Don't worry about it. It should be uniform, right? So what do I do? Write this. Now, how do I make sure this is less than epsilon by 2? Remember, fn is uniformly Cauchy. Therefore, for the given epsilon, there exists a capital N, so that mod fn x minus fmx for m and n greater than or equal to n will be less than epsilon by 2. You understand? Now this is true for every x in capital X. Therefore, independent of it, this fellow is less than epsilon by 2. Do you understand? Right? But I want this also less than epsilon by 2. How do I make this is less than epsilon by 2? Remember, my fmx converges to fx pointwise. So I have fixed an x. You understand? Therefore, there exists an nx, so that if m is greater than or equal to nx, mod fmx minus f of x is less than epsilon by 2. Do you understand that? Right? Now my t, which is a curly leaf, which is equal to fmx, okay, I have to make sure it satisfies this. For this, my m should be greater than or equal to capital N. This has nothing to do with x. You understand that? It is this n is got by uniform Cauchy condition. Okay, this capital N has nothing to do with x. But I want this to be less than epsilon by 2. For this, I want this m should be greater than or equal to nx. You see that? Therefore, this t depends upon x. So what all I have to do is, I can choose m to be, for example, n plus nx. Then m is greater than or equal to capital N. It's also greater than or equal to nx. You understand? Right? Therefore, this will be less than epsilon by 2 by uniform Cauchy condition, and this will be less than epsilon by 2 because m is greater than or equal to nx. You understood that? Sure? Please go through. If you are in little confused, go back to what I did here. Even to prove fx minus gx is greater than, I said I can choose a function whose value, okay, this function may vary. So what do you think I have proved? Let us understand this. Okay, so pause, review, proceed. So how do I write a textbook proof? Let epsilon be given. Okay, f1 uniformly Cauchy. I'm not going to write everything as usual, right? Therefore, there exists a capital N for all m n greater than or equal to capital N mod fnx minus fmx is less than epsilon by 2, right? Okay, and for the same epsilon, okay, for every x there exists nx, a natural number, so that for every m greater than or equal to nx, what do I know? Mod fmx minus f of x is less than epsilon by 2. This is 1, this is 2. You understand this? Right? Now choose, okay, fix x in capital X. Let m equal to n plus nx. Then what do I have? Mod f and n should be greater than or equal to capital N. Then fnx minus fx is less than or equal to mod fnx minus fmx. For this is true for all m, but I am choosing this particular m, plus fmx minus fx. Do you understand this? This is true for all m. Okay, here I don't need any condition on m, but when I want to say this is less than epsilon by 2, I use 1. This is by 1, right? And this is epsilon by 2 less than epsilon by 2. Why? Because my m is n plus nx. So what do you think I have proved? For any given x, therefore I have proved for every x in capital X, fnx minus fx is less than epsilon for all n greater than or equal to capital N. You understood that? That means given epsilon positive, there is a natural number, so that for every n greater than or equal to capital N and for every x in capital X, I have proved mod fnx minus f of x is less than epsilon. That means f1 converges to f uniformly on x. Okay, don't be frightened, go through the proof. Okay, and my suggestion would be, if this is the first time you are going through curry leaf trick, go back to the very starting point of curry leaf where I started doing here. Okay, from this point you again go through, you will understand. Okay, now I said in the classical book what they will do will be like this. Okay, the textbook proof, usual textbook proof will say this is uniformly Cauchy. Therefore, for epsilon greater than 0, there is a natural number n, so that for every m and n and for all x in capital X, what do we have? Mod fnx minus fmx is less than epsilon, right? Therefore, they will say fix n greater than or equal to n and let m go to infinity. Then they will say for all x we have mod fnx minus f of x is less than epsilon, less than or equal to epsilon. Okay, this is how they will write the. Okay, many students are very uncomfortable, and teachers also simply write it without explaining why it's a correct statement. Okay, but that's very easy. Okay, because what we are using is continuity of the absolute value function. Okay, if you had seen my lectures on continuity, I would have done that there also. How do you prove it? Again, actually you prove the continuity of absolute value function using a Curry-Leaf trick, even though people may not appreciate. Okay, you understand? Yeah, right, because let's look at, if an converges to a, you know that we know mod an converges to mod a, right? Now let's look at fnx minus fmx. Right, I am keeping n fixed, therefore where does it go? As m goes to infinity, it goes to fnx minus f of x. You understand? Therefore this sequence converges to this sequence, therefore absolute value of this sequence will converge to absolute value of this sequence. But each of these terms is less than epsilon, therefore the limit will be less than or equal to epsilon. So this is an absolutely correct statement, but many of you may like to use this instead of learning Curry-Leaf. But if you really want to be very confident about analysis, I will suggest you go back. Even though it is a little struggle, it teaches you a very good trick, because analysis means estimate. Estimate means you have to use triangle inequality sometime or the other, and Curry-Leaf tells you how to use it. Okay, how to look for a smart choice of t. Okay, please learn that. Okay, right, so this completes the thing. So I will give an application of this uniform convergence result. Okay, in the last lecture, see I could just give the application, but you know my way of thinking is I always relate to what I have learned earlier, so that I consolidate my previous knowledge, and also it helps me to understand the current situation. So it's a kind of back and forth, always helps you. Okay, this is one thing you have to learn, because people only linearly learn, just leave that, okay, assume that's correct, we have seen it. No, you just compare and contrast, then your depth of understanding is much better. Okay, so why all these things? Do you remember we said if fn, okay, are continuous and differentiable, and if fn dash continuously differentiable, sorry, fn's are continuously differentiable, that is C1, right? And if fn converges, and if fn dash converges uniformly to G, then we said that fn is uniformly convergent. This is by using fundamental theorem of integral calculus. This is what we did in the last lecture. Yeah, so what is our assumption? Our assumptions are fn's are continuously differentiable. Not only differentiable, the derivative must be continuous, because I wanted to integrate fn dash. Okay, I want to consider indefinite integral of fn dash and use fundamental theorem of calculus. Okay, please go back. You know, just because you have seen it and understood, you will refuse to think. That's not what I do. Whenever I do, very quickly I try to spend about a minute or so, go through the argument quickly. If not fix all the details, at least go through that, so that you will feel comfortable. Anyway, my way of doing things. Anyway, all right, let's go. Now what I want to do is I want to prove the same thing without the condition that derivatives are continuous. That is what we want. I have an interval AB, okay, finite interval. Okay, let's assume it's open, so that you know you do not worry about R, and I have fn's differentiable. Okay, and suppose C is a point AB. What are the assumptions? F and C is convergent, or Cauchy if you want. Okay, it converges to some number. I don't care what the number is. Okay, call it lambda if you want, convergent to lambda. Okay, right. 2 and fn dash, okay, converges uniformly to G on the interval AB. Yeah, then what I want to claim is f n converges uniformly on AB, and if I let f equal to limit of fn, then f is differentiable and f dash equal to g. Okay, you should read it as two statements: f is differentiable on J and f dash equal to g on J. But usually I will write f dash equal to g, all textbook. Do you understand? Is it exactly the same theorem? Yes, but what are the things? These are less stringent. The hypothesis I am assuming is less. Why? I am not assuming fn dash are continuous, but I am assuming fn dash converges uniformly and fn c is convergent. All those things are there, but I also wanted fn dash as continuous. That's what I said. Why did I need it? I wanted to form integrals, indefinite integrals of fn dash, and apply fundamental theorem of calculus. Okay, please go back and review. Okay, so if I want to say f1 converges uniformly, say, notice that here I don't even have the function f. Yeah, so what do I do? Now I know, all of you know what to do, right? I have to show f1 is uniformly Cauchy, right? If f1 is uniformly Cauchy, what is that I have to estimate? I have to estimate fnx minus fmx. I have to find a uniform estimate, right? To show it's uniformly Cauchy. Okay, now let's do that. How do I know that? See, the first thing is, the moment you see fnx minus fmx, I can't do anything. But remember, you told me fn's are differentiable and fnc is also convergent, right? So I have a, b, I have some x, and I have c. Okay, and x may be anywhere, right? You understand? Therefore, what is natural is I can apply fnx minus fnc kind of thing. If I do this, what is the thing? I want to use differentiability. What is that you can use? I can use fn dash some xi into x minus c kind of thing. You understand? So I can use mean-value theorem. Okay. Therefore, what I could do, okay, notice this, there is a subtle argument here. Okay. So you may think I can use fnx minus fnc, okay, and minus fmx minus fmc kind of thing. Why? Because notice that fnx minus fmx, and what do I have here? fnc minus fmc. Okay, so in modulus this will be less than or equal to, less than or equal to. So this you can say uniformly Cauchy. This is convergent, so you think you can get an estimate. Do you follow that? I'm just thinking aloud. Yeah, but the interesting thing is I don't want to apply the mean value theorem to this. That's the crucial thing. Because why? Do you see why? Because what I will have is, if I apply mean value theorem, I will get fn dash of xi. This xi will depend upon, for this, okay, this xi will depend upon n, x and c. C is fixed, therefore I can simply say n and x. And here I will, this one will give me as fn dash of xi, but that xi will depend upon what? M, x and c. X and c are okay, but m and n may be different. Therefore this xi and this xi will be different. You follow that? Therefore if I apply the mean value theorem individually, I will get something like this: fn dash of some s minus fn dash of some t, where s and t may be distinct. I can't use uniform Cauchy nature here, fm dash. Are you following? See, these are the kind of things teachers don't explain. They will immediately write the proof. So you, and if you forget, you will suffer. Okay, so this will not work. So what do I do? So the trick was, the trouble was, when I applied mean value theorem to fnx minus fnc and fmx minus fmc, I get some s and t's, and they may be distinct, fn dash of s minus fm dash of t. Then I can't use uniform Cauchy. So what is the trick? The trick is very easy. That is, now look at fnx minus, this is, let me write it like this, fn minus fmx minus fn minus fmc. You understand this? Call this as a function phi if you want. This is something like phi of x minus phi of c. What is phi? Phi is fn minus fm. Therefore, what is phi dash? Phi dash is fn dash minus fm dash. You follow that? Yes? Yeah. So this is what I want to apply. So fn minus fm at x minus fn minus fm at c. Now this is a differentiable function, right? And therefore by mean value theorem, this is equal to modulus of fn minus fm, this whole dash at some point xi. This xi of course will depend upon n, m and x, right, into x minus c. Are you following? Yes. But this is less than or equal to, actually equal to, okay, let me write it less than or equal to fn dash minus fm dash xi minus fm dash xi times x minus c. But remember, x and c are in AB. Therefore x minus c will be less than or equal to b minus a. Are you following? Yes. But what do I know about this? Do I know how to estimate this? So this is a constant now. Do I know how to estimate this? Yes, because fn dash is Cauchy. Because fn dash converges uniformly to g, therefore in particular fn dash is uniformly Cauchy, right? Therefore I can make sure this is less than something like epsilon by b minus a if you want, okay, for n and m greater than or equal to capital N. Are you following? Therefore it get cancelled. So yeah, so how will you write a textbook proof? So given epsilon, okay, choose n, so that for all m, n greater than or equal to n, and x in capital J is the interval, mod fn dash of x minus fm dash of x is less than epsilon by b minus a. Alright, then for all m n greater than or equal to capital N, mod fn x minus fmx, yeah, is maybe let us make it 2. I will say, tell you why 2, right? This will be less than or equal to mod fn x minus fn c, yeah, plus fn c minus fmc, therefore plus fmc minus fmx. Do you understand this? Therefore this equality less than or equal to mod fn x minus fn c plus mod fn c minus fmc plus mod fm x minus fm c. Yeah, right. But that's not what I wanted, is what we saw. How did I want to do that? This is equal, but this is not what we wanted. What we wanted was, we wanted to rewrite it. How did I rewrite this fmx? See, you can see I'm thinking so that you will learn how to do that, fmx and fmx. Therefore I can write this as mod fnx minus fmx, okay, minus fnc minus fmc. Yeah, and plus this one. Do you understand this? I'm grouping terms now. Yeah, right. So this is less than or equal to mod fn minus fm of x minus fn minus fm of c plus fn of c minus fm of c. Yeah, right. So by this, by 1, okay, I know this is less than or equal to epsilon by 2 into b minus a into b minus a plus this one. So what I can do, since fn of c converges to fm of c, I can also choose n such that 1 and fn of c minus fm of c, this is convergent, therefore in particular it's Cauchy, it's less than epsilon by 2 for all n m greater than equal to n. So you see that textbook proof should start with two statements, 1 and 2. What is that? Given epsilon, choose an n using uniform Cauchiness of f dash, fn dash, right? And if you want, there is an n1, similarly there is an n2 for fnc minus fmc less than epsilon by 2. Choose n to be maximum of n1 and n2, therefore there is a single n such that both these things are true. Yeah, therefore this is also less than epsilon by 2. So therefore epsilon. So what do you think I have shown? I have shown that fn is uniformly Cauchy. Okay, pause, review, proceed. Okay, so this part I still have to prove this. Okay, this we will do in the next lecture because it's already some time, so it's good to stop here. So the application is only this much. What is the application? If fn's from a b to r are differentiable and there is a point c in the interval such that fn c is convergent and fn dash converges uniformly to g, then fn converges uniformly on ab. That's all. That's just okay. This extra we don't want. This is where the theorem. So have I proved the theorem? Yes, I simply said fn is uniformly Cauchy, but before the last theorem said anything uniformly Cauchy is uniformly convergent, therefore the theorem is proved. Do you understand? Okay, I hope you enjoyed the lecture. So I hope you enjoyed the lecture. Yeah, please go through it and go through the curry leaves trick. I think this is the first time I'm taking a lot of pain to explain the curry leaf trick. Even though in some of my books it may be there, and in earlier some lectures also I might explain. I do not remember, but I don't believe that people are systematically going through all my lectures, right? Some of you may not even look at anything, but you are intrigued or you are puzzled or confused or you're not confident about uniform convergence, so you started looking only this series of lectures, right? It's possible. Then curry leaf trick you may not have learned from me at all, then you may be at a loss. So that's why I took some pain. Please go through it. I hope all of you enjoyed. Okay, good. Stay healthy, safe. We will meet again.